Okay, this is a quick example of how to do a Hoffman transfer. Of course, they're simple, they're easy. We're only going to be dealing with uh, we're going to be dealing with 3 orbits total, and I'll use the Earth as an example. We're in some sort of circular orbit around the Earth, and we want to end up in a different circular orbit around the Earth. So here we have 2 perfectly drawn circular orbits around the Earth. Each orbit has its own properties. So there's the radius of the inner orbit, and separately there's the radius of the outer orbit. There's the period and velocity associated with the inner orbit, and then there's the period and the velocity associated with the outer orbit. And here I'm using subscript I for inner and O for outer. So the inner orbit has an inner period and an inner orbit velocity, VI. The outer orbit has an outer orbit radius, R, O. And we don't even care about the periods for these orbits. But sometimes the problem begins with me telling you the value of the period, and then you have to go figure out the 2 things that we do care about. We care about the radius and we care about the velocity for these 2 circular orbits. So kind of as a first task, first order of magnitude, I don't know, not order of magnitude, first sequence to do is to calculate the radius and velocity for each of these 2 orbits. They're both circular. I'm going to make a horrible problem just because you need to practice, and that will be I am in a orbital period of 1.6 hours around the Earth, and it's an equatorial orbit, and I want to transfer to a circular orbit that is exactly 3.2 hours. And this is because I always have in mind my impulse engine space transportation architecture, and the problems I'm creating, the examples are somewhat related towards that long-term goal. So if I have this as my period, I need to turn this into an orbital radius before I can do anything else. The equation is t squared equals 4 pi squared r cubed over gm. And I would have to rearrange the equation and say r is equal to the cube root of gmt squared divided by 4 pi squared. Okay, so in this situation, what I would type in is r is equal to the cube root of g, and for the Earth, well, g, of course, is 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. The mass of the Earth is 5.974 times 10 to the 24th power kilograms. And I'm putting both of those into my calculator memory so that I don't have to keep typing them in over and over and over again. So central body set to be Earth, and then let's quit. Okay, so G and M are in my calculator memory. So here I can just type G and M, but for the inner orbit period, I have to convert hours to seconds. So open parentheses, 1.6 times 3,600 seconds per hour, close parentheses, and now I have to square this period. Still underneath the radical, I have to divide by 4, and I also have to divide by pi squared. So I power up my calculator, and the way I would do this is open parentheses for this entire expression, alpha g, alpha m, open parentheses, 1.6 times 3600, close parentheses, quantity squared, divide by, and I have some students who are not comfortable with saying divide by 4, divide by pi squared. So this time I'll do it with open parentheses, 4 times pi squared, close parentheses, and that takes care of the denominator. Now close parentheses to enclose the entire expression underneath the radical sign. And for the radical, it's caret, meaning raise it to the power of. I type in 3, which would cube it, but then I press the x minus 1 button, which means, oh, now it's 1/3 power. So this is how I type in to find the cube root. Enter. Boop. There's the answer. The orbit radius for the inner orbit is, well, okay. I like expressing things in kilometers, and I don't feel like counting all those digits, so I'm just going to divide by 1,000, enter, and say, oh, the inner orbit radius is 6,945 kilometers. I need that piece of information. So there it is written down. For the outer, let's see, what else do I need to know about this inner orbit? You know what? As long as I have the value in my calculator, how about if I multiply it by 1,000 and turn it back into meters? And then say, as long as I'm here, I also want to calculate what my orbital speed is. My orbital speed is given by the square root of gm over r, the orbit radius. Since I have r on my calculator display and g and m are in memory, I'll just do it while it's here. So second square root alpha g alpha m divide by second answer recalls this value. So that's why I turned it back into meters. Now that it's back into meters, I press the enter key, and it's a totally reasonable number to someone who's been doing this for so long that I can look at that and say, oh, yeah, that seems right. 7,576 meters per second. Okay, so this is the inner orbit velocity, and this is the inner orbit radius. Now I do exactly the same thing for the outer orbit. The outer orbit has a period of 3.2 hours. So for the outer orbit radius, it's going to be the cube root of gm, open parentheses, 3.2 times 3,600, close parentheses, squared, divided by 4 pi squared. All right, so on my calculator, one thing I could do if I really felt like it, I could just keep backing up, recalling previous equations, and say, look, all I need to do is change this 1.6 into a 3.2, and the rest of the expression is already good to go. The cube root of gm 3.2 converted to seconds, 3.2 hours converted to seconds squared, divided by 4 pi squared, enter. Boop. There's the answer in meters. Now, before I even write it down, I'm thinking, last time I needed that to calculate the outer orbit velocity. So I'll write that one down first. That is the square root of gm over the outer orbit radius. And on my calculator, maybe I shouldn't be so lazy. In my head, moving the decimal point 3 places to the left, I see this is 11,024 kilometers. I should just write it down. 11,024 kilometers is the outer orbit radius. For the velocity, that would be square root of g m divided by this answer, enter. Again, totally reasonable looking number, 6,000 13 meters per second. Nice. What do I do with this information? The German engineer Herr Hoffman in 1925 or whenever it was established that the lowest energy method to switch from one circular orbit to another circular orbit around the same central body is to go along an elliptical orbit that just touches each of the two circular orbits at one point. So you can't start inside, you can't start outside, you have to start touching the inner circular orbit. So at that one tangent point, you build an elliptical orbit that goes out and touches the outer circular orbit at just one point. And look at this beautifully drawn elliptical transfer orbit. So, in name of the guy who figured this out, we call this a Hoffman transfer orbit. It is half of an ellipse. All orbits are conic sections. So if you did nothing, you would just continue in whatever conic section you're in. Circular orbits like the moon going around the Earth go on for billions of years, or at least hundreds of millions. Billions. The Earth around the sun, billions of years. An elliptical transfer orbit, billions of years if there's no friction. So to change from one orbit to another, you need to make a change in your velocity. We have figured out that on the inner orbit in this example, you're starting off going at 7,576 meters per second. To climb out of Earth's gravity well, to end up at the outer circular orbit, well, the outer orbit we said is going on a velocity of 6,013 meters per second. So interestingly enough, to end up going slower, you have to speed up. Mathematically, that doesn't sound like what you learn on the surface of the Earth. On the surface of the Earth, if you're going 75 miles per hour and you want to slow down to 60 miles per hour, you slow down, you don't speed up. But in orbits, if you're going 7,500 meters, if you're going 7.5 kilometers per second, and you want to end up going 6.0 kilometers per second, you have to speed up and then speed up again so that you end up going that slow. Crazy, but true. So now we need to build this elliptical orbit. And we know the two things about it that we need to build this orbit. We know the minimum distance from the Earth to this elliptical orbit. That's called the perigee distance when we're orbiting the Earth, or periapsis in general. And we know the distance to the farthest point on this transfer orbit. That is called apogee if we're orbiting the Earth. Perigee is the inner orbit radius. Apogee is the outer orbit radius. And that's why we needed to calculate those values if they weren't handed to us. I gave you period, you needed to convert that to orbital radii. I gave you periods, you needed to convert it to orbital radii. So in this example, we now just go through the mechanics of calculating what we need about this elliptical orbit. And the details are this. The semi-major axis is represented by lowercase letter a, and it is the average of the two circular orbits. So if you take the radius of the inner orbit and the radius of the outer orbit, add them together, divide by 2, you'll have the semi-major axis. Woohoo! So if I take 6945, add to that 11,024, that's the major axis. Divide that by 2, and that is the semi-major axis. And my calculator says beep, 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 beep. It is 8,980, oh, I'll call it 5 kilometers. I'm not going to do this to 5 sig figs. This is already to 4. Okay, so there's the semi-major axis. The beauty about elliptical orbits is that their average speed is the speed of their average orbit radius, the semi-major axis. The semi-major axis is their average orbit radius, and their average orbital velocity is gm over a. That's semi-major axis. So if I go square root of alpha g, alpha m, divided by, and here I need to be kind of careful because this is in kilometers. So if I want to use that number, I would have to go open parentheses, second answer to pull this off of the display, times 1,000, close parentheses. And now it's converted it from kilometers, without rounding it the way I had, back into meters so that I can plug it into this equation, and boop, the average orbital speed on the transfer orbit is 6,661 meters per second. Nice. Now, the next part that I grind out is to calculate the speed at which I'm moving when I'm at perigee. The formula for that is the velocity of perigee is equal to the average velocity on this elliptical orbit times the square root of the ratio of apogee divided by perigee. Often students mix up which one is on top. They think, oh, if I'm after perigee, I should put perigee on top. But actually, it's the other way. At perigee, you're closer to the Earth and you're moving faster. See, faster than when you're farther away. So you need to build the ratio so that the bigger number is in the numerator and the smaller number is in the denominator. In this case, I would take the number in my display, there's my average velocity, and go times square root of, in the numerator, I type in 11,024. In the denominator, I type in 6,945 and enter. My calculator says the average orbital velocity at perigee is 8,392 meters per second. And as I would expect, that is even faster than my inner orbit velocity. Makes sense. I'm falling towards the Earth, speeding up as I approach the inner orbit. So yes, I'm going too fast to be in this circular orbit. I end up going away from the Earth, continuing on my elliptical orbit. Makes hideous sense. While I'm at it, I need to calculate the apogee velocity. And that is the product of the average orbital speed of the transfer orbit times the square root of this ratio flipped. Now the perigee radius is divided by the apogee radius. Perigee is smaller than apogee. This number is smaller than 1. Square root of number smaller than 1 is a number smaller than 1. So my apogee velocity is going to be less than my average velocity. And I don't really have a convenient way. I can't use answer divide by because that would put in the wrong value. What I can do is just re-enter the average velocity, 8,392 times the square root of And this time I'll type in 6,945 divided by 11,024, enter, and that looks wrong. It looks wrong because I typed in the perigee velocity when I was supposed to type in the average velocity. My bad. So I'm going to replace my mistake with the correct value. Instead of typing in 8392, I was supposed to type in 6661. Enter. Okay. Apogee velocity is 5,287 meters per second. Oh, sorry. Kind of want to zoom in, kind of want to focus and explain. I'm in this example, I'm starting in a circular orbit where I'm going at 75, 76 meters per second. To switch onto the perigee of the transfer orbit, I need to end up going faster. I need to go 8,392 meters per second. Well, I'm not going that fast. So the change in velocity that I need, I call that delta V1, and it's by subtraction. So 8,392 minus my inner orbit velocity, which was 7,576, is 816 meters per second. I need to speed up by that amount to switch from the inner circular orbit to the perigee of the Hoffman transfer orbit. I fly away from the Earth, climbing up its gravity well, slowing down, slowing down, slowing down. Now I'm going too slow to stay up here. Like a ball thrown into the air, it's time to fall back down. But before I fall back down, I want to switch onto the outer circular orbit. Well, to be in the outer circular orbit, I need to be going at 6,013 meters per second. But I'm only going 5,287 meters per second. So I fire up my calculator and I ask it, what is 6,013 minus 5,287? And it says, oh man, I need another 726 meters per second. For rocket fuel calculations, we need to know what is the sum of these two values. 816 and 726 add up to 1,542 meters per second. That is the total amount of change in velocity I need if I really want to go from inner orbit to outer orbit. The last piece of information that I ask of you students is how much time does it take to go from inner orbit to outer orbit? To get that answer, I have to calculate the orbital period of the elliptical orbit. And for that one, T is equal to this 2 pi square root of r cubed of a cubed over gm. Oh man. So I'm just going to go, what is 2 pi square root of, and I'm going to put in the semi-major axis, which I said is 8,984,500 meters, and I have to cube that. So cubed, and in the denominator, I still have, so let's divide by, open parentheses, alpha G, alpha M, close parentheses, and I think I'm good to go to hit the enter button. Boop. So there is the period of time of the elliptical orbit. T is 8,475 seconds. Well, that's the time to go from perigee up to apogee and back to perigee. I only need half of the orbital period. So I'm going to divide this by 2 and list this as my time of flight, TOF. In seconds, it's 4,238 seconds. Now, I would expect it to work out to be some number between half of 1.6 hours and half of 3.2 hours. So when I divide this by 60, that tells me it's 70 minutes. 70.6 minutes. Does that seem reasonable? That's 1.1-ish hours. Yes, to me that seems reasonable because half of 1.6 is 0.8 hours, half of 3.2 is 1.6. So I'm expecting an answer somewhere between 0.8 and 1.6 hours. And this looks like it's like 1.1 or so. So I have mastered aerospace engineering thanks to a guy whose name escapes me right now. Gosh, he gave me my first lesson in this stuff when I was working at McDonnell Douglas. Dr. Forgotten.